and welcome to the latest in our series of live Mighty Low Carbon Energy Center webinars. Today's webinar is concerned with the choices we make in the coming decades in the course of transforming the global energy system and the important consequences they may have for greenhouse gas emissions and effective policy. I'm Robert Stoner, the Deputy Director of Mighty for Science and Technology, and I'll be your moderator. As usual, our intention in presenting these seminars is to cover a range of topics drawn from ongoing work within all of Mighty's low carbon energy centers and a few drawn from outside them. We want you to know what we're up to at MIT and what we think is especially interesting and important as we work our way toward a globally decarbonized energy system. And because we want to engage and hear from you, we'll reserve time at the end of the session to answer your questions. Please pose those questions at any time using the Zoom Q&A feature. We understand that not everyone will be able to join us live, and so as usual, we'll be recording this webinar so that it can be viewed offline by you and hopefully your colleagues. Feel free to forward it. Since the day we first gained control over fire a number of years ago, we began using energy in intentional ways to improve our lives. We've been creating an energy system that has grown steadily more complex and interconnected with our economy. As sectors of the economy that have been historically more or less independent, such as transportation and power, become coupled through the electricity system, the consequences of choices within one sector, whether driven purely by economics or policy or both, may influence emissions within others. What that means is that our efforts to decarbonize that energy system, that is to reduce associated greenhouse gas emissions, can lead to outcomes that are very hard to predict quantitatively. At Mighty, we've been developing a number of large-scale modeling tools to help inform effective policy to achieve desirable economic and emissions outcomes. Our speaker today is Dr. Emery Genscher, an MIT research scientist and one of the leaders of Mighty's Energy Systems Modeling Group. His research focuses on emerging and conventional energy technologies and their policy implications using multi-scale modeling and optimization techniques. For the past several years, Emery's led a growing team of postdoctoral researchers and students who are developing SESAME, the Sustainable Energy Systems Analysis and Modeling Environment. He's going to describe SESAME for us today and show us how it can be used to address contemporary policy questions. Emery, thanks for joining us today and take it away.
Thank you, Rob, for the introduction, and thank you for also motivating the talk quite extensively. So today I will be talking about SESAME and what we have been doing over SESAME. And for some of you, I know this will be more like an update, but for the some guests, hopefully this will be a completely new talk. So as Rob mentioned at the beginning of the introduction, basically we are seeing a huge change in the energy system. And one of the main characteristics of this change is all the different subsectors of energy system converging, which means we are now seeing more connection between industrial sector, power sector, transportation, and residential sectors. So one of the obvious observations is, of course, for the EVs, electrification of transportation, especially for light-duty vehicles. And we are seeing across the globe new regulations about increasing the EV penetration, or maybe in some cases actually banning internal combustion engine vehicles to completely switching to EVs. And similarly, we are seeing quite a lot of trends about using hydrogen in many sectors, especially for the deep decarbonization purposes. And my colleague Darik had a webinar a couple of weeks back about some ongoing work on hydrogen. So when we look at this system, one of the challenges that we are seeing is, so far, the modeling, energy system modeling field has been focusing on individual sectors. So there are very detailed models about power sectors, similarly for industrial transportation. And when we start having these linkages, that wasn't common a couple of decades back or years back. Actually, we need to develop new methods and new tools to understand this challenging, new complex system. And the second point I want to emphasize is about the decarbonization. So one of the pillars of energy transition is, of course, decarbonization. And when we are discussing decarbonization, we really need to understand different and all emission sources. So famously right now, it is classified as Scope 1, Scope 2, and Scope 3 emissions. But without having any labels, if we look at the value chain, supply chain of different transportation options in this particular graph, you will see we can start from a variety of resources, oil, biomass, coal, wind, solar, natural gas, to have the same end goal, transportation from point A to point B, or carrying a load from point A to point B. And in all of these supply chains, we are seeing multiple emission sources that's shown in gray arrows, which means that when we want to have a decarbonization pathway, we really need to account for the entire life cycle emissions, including exploration, transportation, and as well as the end use case. And here you can see when we compare, for example, EVs with internal combustion engine vehicles, only comparing tailpipe emissions is not enough, is not sufficient, because it all depends on how we produce electricity if we want to have a comparison between internal combustion engine vehicles and EVs. And I will give an example about this in more detail. So over the last couple of years, we've been developing this tool called SESAME to basically provide insights on the feasibility, scalability, and emission reduction potential of various technology pathways. And in 4 points, the main purpose here to assess and compare technology options, perform technology and system scenario analysis, explore the implications of policy dynamics, and perform cross-sector comparisons. So in building this tool, we really wanted this tool to be accessible, not only usable by expert users who have been working in this area for many more years, but it is more accessible and more easily usable by any people. And here, this is just showing you the modular structure that we've developed. So this can be used as the matrix that is underlying the SESAME platform. And you can see we have defined the entire energy system in terms of 6 life cycle stages, starting from upstream, midstream, process, carbon capture, utilization and storage, gate to user, and end use. Each one of these vectors are looking at different options. So in the upstream case, you can see the resources from renewables to fossils. And in each one of these modules, you will see many different sub-modules. Like for natural gas, we have different options, conventional shale gas. And even in these ones, you can go to different locations, so on and so forth. Midstream is looking at how we can transport these resources to the processing step to be converted to power or other products like gasoline, diesel, hydrogen, iron and steel, so on and so forth. And CCUS is one of the key focus areas in our low carbon energy centers, because to have deep decarbonization, we really need to incorporate carbon capture in our technology portfolio. And that's exactly why we have dedicated an entire vector for different CCUS options. And gate to user is transporting the products to the end use, and under end use, we are covering major end use sectors like electricity, heat, fuel for transportation, and chemicals. And so far, we've been developing this tool in different platforms, and now we are close to getting ready to launch our open access platform to perform pathway and system level analysis. So this version will be a web-based, web browser-based tool in which you can perform all the analysis that I will be discussing in this talk. But just to give you an overview, so you can build different pathways, you can perform life cycle assessment, techno-economic assessment for all these pathways. And another analysis type is system-based analysis, which is represented by fleet model for vehicle fleet and power system model. And also we've been monitoring the electricity demand due to COVID for the entire US. And this is also live, so you can go to sesame.mit.edu and you will see there is a COVID dashboard. So it's not fully developed, but at least you can follow the electricity trends by going to this link. I want to give you a couple of examples on how we can use this metrics and how we can use our tools to get some insights about the changing energy system. And I will start with building a natural gas to electricity pathway. And also I want to show you how this is working in the backend. So basically, when you start building a pathway, and you can build pathways in either direction, either from upstream to end use or end use to upstream. Each one of these modules has linkages to the next and previous steps. So let's start from natural gas conventional, connect to compression to adjust the pressure for the pipeline transport, and send it through pipelines to a combined cycle unit. And in the combined cycle units, we produce power, and it is transmitted and distributed to be used as electricity in any end use application. And we can call this pathway 1, natural gas to electricity. Now let's look at the user interface, how this works. Basically, so this is an earlier version, which is currently working version of Sesame. And here you can build the same pathway by using drop-down menus with different options. And you can have the results for different loadings of part loadings of combined cycle units as well as gas turbine units. So the reason I wanted to show you a variation of emission intensity for combined cycle units and gas turbine units under different loadings is because it is affecting its efficiency, which is eventually affecting its emission intensity. So when we look at these graphs, the first 4 cases are combined cycle units, and the second 4 cases is the gas turbine units. Here I've looked into operating these units from 100% loading all the way to 40% loading, which is a very common part load operation right now. And for gas turbine units, I have calculated the same part loading. So what I wanted you to see here is basically when you operate combined cycle units, a part load, you are increasing the emission intensity by almost 20%. And for gas turbine units, this part loading is increasing the emission intensity almost by 50%. So to understand what kind of impact it has over the operation of an entire grid, we also need to understand the grid composition and also how in reality each one of these plants are operated. To look into this, we really need to use real world data. And in the US, some of these data sets can be found in publicly available sources. And in Sesame, we have actually embedded all the fleet level, unit level data in generation as well as emissions for the entire US fleet, which is approximately 10,000 units. And here you can see the operation of one representative combined cycle unit in California. So here you can see from the hourly load profile, these units are cycling quite frequently. And you can see this is going for, between 40% and 100% quite frequently. More interestingly, actually, we are seeing quite a number of startups and shutdowns during this period of time. So there are some shutdowns even in a day or so, or we have more shutdowns in the longer periods of time. So there are a couple of implications of this. First of all, these are becoming more idle units as we are not operating at base load, which they were supposed to do. Secondly, we are operating at an inefficient regime because we are now doing these cyclings, part loading, as well as startup and shutdowns. And third one, when we want to decarbonize these kind of plants, the dynamic operation of carbon capture facilities is quite challenging. And right now, the existing carbon capture technologies, amine-based technologies, operates like chemical plants, which are supposed to be operated in under steady state conditions. And when we see cycling, these kind of change in operation, they will be unable to operate when you retrofit these plants with carbon capture. But actually, we have a project currently that's been recently funded that we are looking at flexible carbon capture operations, and it's led by Howard Herzog. This will be a very exciting project. So when we talk about bringing together all these data sources, this wasn't a very easy task, because even though these data sources are publicly available, all the information you require is not readily available in one single database. So what we had to do was to match different data sets and collect information from different databases, namely eGrid dataset and SAM's dataset. And now we have created a single database which has all the unit level information as well as hourly load profiles for many years, moving back 15 years, moving back, that is embedded in the SESAME platform, as well as it will be accessible through our open access platform. Now we have unit level data on hourly emissions, hourly generation, nominal capacity values, so on and so forth. And with the easy user interface, you can play around and do a bunch of analysis. And I want to, before showing the type of analysis you can do, I also want to revisit this previous graph about the cycling hourly load profile of a combined cycle unit, and show you what fraction of time is actually spent in part loading. So here you can see with these orange dots, we are looking at the loading ratio, which is between 40% and 80% for this particular unit. And you can see that actually it is cycling all the time. And there are many points throughout the year that is zero load or very low loading ratios. And these lower loadings that you are seeing here, approximately 20%, are mostly startup or shutdown. So since we have hourly data, we are not able to capture sub-hourly operational trends. So this is from a recent manuscript that we have submitted, basically using all these data sets from the mesh data and also using the SESAME platform. We have looked at how the operation of combined cycle units and gas turbine units are changing over the last, from 2011 to 2017, and where these units are spending more time, and also how the emissions are distributed between these different operation modes. So here we've classified these operations under 4 categories: startup and shutdown, part loading, which is lower than 80%, nearly full load, which is higher than 80%, and full load 100% or nameplate capacity. So here the 2011 generation is shown in blue, and 2017 generation is shown in purple. Similarly, the bar charts are showing the total generation, which is shown on the left, and curves are showing the total emissions, which is shown in the right hand side vertical axis. And so here we will see 2 comparisons. The first one is annual comparison for a particular unit, combined cycle and gas turbine units. And the second comparison I want to make is between combined cycle units and gas turbine units. So the first observation we'll see is that for combined cycle units, the startup and shutdown time has changed. And here the x-axis is the hour of the day. So earlier in 2011, we were seeing startups in the early morning hours, which is shifted towards afternoon hours now. And similarly, we are generating more in the morning hours from combined cycle units from startup and shutdown, which is moving towards afternoon hours. For part load operation, you can see the part load operation was quite low for earlier years. So we were barely seeing part load operation during the day because it was mostly operated as base load. And we are seeing a huge increase in part load operation from combined cycle units in 2017. And you can see on the right-hand side, actually, the emissions from these operations are also increasing quite dramatically. So it was approximately 0.5 million tons, and now it is close to 0.7 million tons. And the reason this part load operation, increase in part load operation is important is because actually when you operate at part load, your efficiency, as I shown in the previous graph, is lower. So even though we are seeing higher emissions, we are actually spending, you can see we are almost getting the same amount of total electricity generated from these units. And nearly full load is kind of representing the base load operation, and shallow cycling close to full load operation. And you can see it was more in 2011 because these were operated more like base load, and it is dropped especially during daytime for combined cycle units in 2017. Same for full load. The second interesting observation that we'll see for the gas turbine units is across the board, we are seeing an increase in generation and emissions from gas turbine units from 2011 to 2017. So this is partially due to having more intermittent renewable sources in the generation mix, as we move from having couple of percentage to more than 15% solar in the system. We see the famous duck curve trends. So we don't have, we have a lot of solar generation during the day, and we need backup during the afternoon hours. So one, of course, the consequence of these trends is on the emission sides, but also this implies the requirement of massive energy storage capacity in a decarbonized power system. So basically, if we are thinking of completely moving from fossil resources to renewable resources, all of these services provided by combined cycle units and gas turbine units to meet and balance the grid in the afternoon hours needs to come from energy storage, different energy storage options. So it can be either batteries or thermal energy storage or other energy storage options, but we will need a massive energy storage to meet all of these extra demand when we don't have enough renewable energy. And the second example I want to give is from transportation sectors. And at the end, I will also connect these two transportation sectors and the trends we've seen in the renewable power and electric power system. And for transportation sectors, we can start with building a normal internal combustion engine vehicle pathway, starting from crude oil, a conventional crude oil transported by pipelines or refined in refineries to produce gasoline and transported by pipelines, and finally it's in the gas stations to be used for light duty vehicles. So here, the one simple example of analysis we can do is calculating the life cycle assessment of light duty vehicles using gasoline. And here, this graph is looking at gram CO2 equivalent per mile driven, and it includes all the life cycle stages from upstream all the way to end use. One missing piece that you will see here is this is operational life cycle emissions, meaning it doesn't include the vehicle manufacturing. So vehicle manufacturing is traditionally does not contribute as much to the overall life cycle emissions, but as we move to new vehicle types like battery electric vehicles and fuel cell electric vehicles, actually vehicle manufacturing starts to becoming an important part of the overall emissions. So to address this issue, actually we can also look at detailed car emissions, and here we can do operating emissions only, as well as vehicle manufacturing emissions that includes changing the batteries, manufacturing batteries, so on and so forth. But this particular one is only looking at operating emissions, similar to the previous one, and it looks at fuel production as well as tailpipe emissions. And for electric power, so battery electric vehicles, we are looking at different states and based on different compositions, and you can see depending on the emission intensity of the grid, battery electric vehicles overall life cycle emissions can be quite different, almost by a fact, it can vary by a factor of 3 or more. And we see internal combustion engine vehicles dominates the overall emissions by having the highest emissions among hybrids and battery electric vehicles. But actually, I want to show you results from our recent study of insights into future mobility. And this is a nicer, cleaner comparison of different powertrains, internal combustion engine vehicles, hybrid electric vehicles, plug-in hybrid electric vehicles, battery electric vehicle, and fuel cell electric vehicles. And here, with green, we represent the vehicle production. The blue is fuel production and purple is fuel consumption. So a couple of important observations here is, first of all, basic assumptions. For battery electric vehicles and plug-in hybrid electric vehicles, we use the average carbon intensity of US electricity. And the second important assumption in this figure is that we are using hydrogen from steam methane reforming without carbon capture. And the one observation we will see is about the vehicle production and how the vehicle production contribution is increasing as we move from internal combustion engine vehicles to vehicles having larger batteries. So you can see in battery electric vehicles, we are seeing almost a 30% increase due to vehicle manufacturing relative to internal combustion engine vehicles. Having said that, we still see a huge benefits relative to internal combustion engine vehicles, almost 55% reduction in overall life cycle emissions for the US average grid. The second observation that I want to highlight here is the other powertrains, hybrids, plug-in hybrids, and fuel cell electric vehicles. As you can see from this graph, actually they are quite comparable to each other. And they have a similar life cycle emissions, which is also almost 40% lower compared to internal combustion engine vehicles. Of course, there are a couple of important sensitivities that we need to explore here. One is the comparison of battery electric vehicles and hybrid electric vehicles, because hybrid electric vehicles will not depend on the emission intensity of the grid, but battery electric vehicle emission intensity can go up if we have a different grid mix and the emission intensity of the grid is different. And the second one is about fuel cell electric vehicles. This results is very sensitive to how we produce hydrogen. If we are producing from completely renewable sources, this can go significantly down to less than 100 grams CO2 equivalent per mile. Versus if we are using electrolysis with grid electricity, this bar can go higher than the internal combustion engine vehicles. And also we can use carbon capture with steam methane reforming or coal gasification, so on and so forth. All can be quite significantly change its ranking relative to other powertrains. And all of these results can be found in this report, and you can go to this link to download the report to read these results as well as much more from this study. So I also want to discuss this battery electric vehicle versus hybrid electric vehicle discussion on a US map. And this is state by state looking at this comparison. And as we go greener, we are seeing a more advantage over hybrid electric vehicles for battery electric vehicles. Meaning if we are in a state like Washington, where the majority of the power is provided by by hydropower, the battery electric vehicles are extremely advantageous because basically there is very low emission coming from electricity generation, and we can continue looking at other green states like California or Massachusetts, Vermont, so on and so forth. And in all of these regions, using electric vehicles, battery electric vehicles, can show a significant reduction in overall emissions, and it can really help the decarbonization of light duty transport sector. But if we are in other states or in other power systems in which we still have coal in the mix, or the emission intensity of the grid is not as clean, then actually switching to hybrid electric vehicles can benefit more relative to battery electric vehicles. And some examples is Indiana, Ohio, Utah, where the coal is still contributing significantly to the power generation. And in these states, actually, the advantage we will be getting driving hybrid electric vehicles is more than switching to battery electric vehicles. And this is a static snapshot of how we can use these kind of analysis and a tool like SESAME. But I also want to highlight more details about how we charge, how we drive, and what kind of contribution each one of these parameters can have over the life cycle emissions of battery electric vehicles. So here I wanted to compare two green states, California and New York in this case. And I want to show, first of all, the generation mix and how it is different between these two systems. And from the color code, you can see both has similar emission intensities, but the composition of these grids are quite different. So in California, we are seeing a huge solar, and also as we've discussed in the previous slides, the midday generation is mostly dominated by solar generation, which is increasing every day. And when we switch to New York, the generation is mostly balanced between hydro, gas, and nuclear. And what we observe here is that nuclear is contributing quite substantially as a base load, which is significantly driving down the emission intensity of the New York grid. And when we look at the percent of total generation, so you can see the solar's contribution during daytime in California system, which is quite significant. And also we are seeing a dip in gas generation during the same time because we don't need that much power in the grid. So when and we either cycle down, turn down, or shut down these plants during these periods of time. And when we look at the New York system, actually we see almost steady nuclear generation and gas generation, which is complementing each other. And hydro is quite stable, and we are seeing also increase in wind generation. Now, since we are interested in the emission intensity of these grids, we can look at the hourly life cycle and operating emissions. So due to increase in solar during midday, we are seeing a decrease in the overall emission intensity during these time period. And you can see the emission intensity is going down significantly during midday for the emission for the California grid. And when we switch to New York, we don't see that trend, but we see a emission intensity decrease during early morning or overnight. And this reason, the reason is from the generation, you can see we rely more on nuclear and less on gas turbines. So we are seeing this decrease. So the implications for charging is basically, if we are in California, then a midday charging will get us the most benefit of driving a EV, because the emission intensity of the grid will be the lowest. But if we are in New York, then overnight charging will get us the highest benefit in terms of decarbonization. And basically, we have all of these similar results for every location in the US. And depending on where you are, even the time of charging will have a huge impact in decarbonization. And to really understand all of these systems, we need to use scenario analysis tools like SESAME to explore different options. And as we move forward, we need to do this more and more frequently to really understand what will be the consequences of different choices. And these are still looking at one vehicle emissions. So what we are really interested in is, from a fleet perspective, what will be the emission consequences of switching to certain powertrain options or certain fuel alternatives. And to address that issue, we have also built a vehicle fleet model that can take different scenarios and calculate the energy use by fuel type as well as emission by for different scenarios. And here you can either create your own scenarios, or you can use any scenarios from any report like EIA's, IEA's reports, Bloomberg's energy reports, so on and so forth. And you can play around with the assumptions about the penetration of different vehicle types, emission intensity of the fuel types, and all of these analysis is also connected to the pathway level analysis. So basically, if you have a new technology, either a vehicle or a fuel production type, you can see the impact of these advancements from a fleet perspective. And also you can calculate the life cycle greenhouse gas emissions for the fleet. So about the fleet, I wanted to give you an example from a recent news about the California governor signing order banning sales of new gasoline cars by 2035. So we have done two extreme cases just to demonstrate how much of a difference it can make. But actually our results show and raise more questions than answers, and Ian Miller has done all this analysis. And if you have any questions, please feel free to reach out to him. So here we are comparing two projections. The first one is EIA's annual energy outlook projection, which is business as usual. And the second option here is banning internal combustion engine vehicles starting in 2035. So let's first look into annual energy outlook projections. The first graph is looking at the sales, total sales in million by vehicle type. The second chart is looking at the fleet, the overall fleet, and how it is changing. The third panel is looking at the fuel use in terawatt hour, and the fourth one is looking at operating life cycle emissions. So this doesn't include vehicle manufacturing. So first, let's look at and understand what the business as usual case for California from annual energy outlook. So as you can see, we are seeing some increase in battery electric vehicles, but the sales is still dominated by internal combustion engine vehicles. And we see that the fleet is almost completely internal combustion engine gasoline vehicles. So we see a decline in fuel use, although we see an increase in the total fleet. So it is going up from 30 million to almost 40 million, but we are seeing a drop in overall fuel use from 450 terawatt hour to 320 terawatt hour. And this decline is mostly due to fuel economy improvement of fuel cell for internal combustion engine vehicles and lightweighting of these vehicles that's expected over the next couple of decades. And when we look at the emissions, when we consume less fuel, of course, we will be seeing a decline in emissions, but it is not dropping quite drastically as we expect to see in California system. So now let's look at the ban case, which is the new regulation case. So in this case, actually, we will have, starting from 2035, we will not see any internal combustion engine vehicle sales, but it will be, and in this particular one, we've assumed that this will be replaced by BEVs, but actually the order also allow using hybrid hydrogen fuel cell electric vehicles, because it is specifically saying that it should be zero emission, but not necessarily battery electric vehicles. But in this case, we are assuming it will be battery electric vehicles, and we assume a linear decline from today to 2035 in internal combustion engine vehicle sales. These are rough assumptions, and of course, we can play around with any of these. In this case, the fleet in 2035 will be still dominated by internal combustion engine vehicles, as most of these vehicles stay on the road for 20 years, 15 to 20 years. But after 35, we will be seeing a huge increase in electric vehicles, and this will be translated in the fuel use and electricity use. So when we look at the fuel use, we will be looking in an additional 160 terawatt hour requirement by 2050 to meet the demand of electric vehicles. And just to give you a comparison, this is 80% of today's California generation. So it is a significant increase in grid capacity. Of course, the second question is, can we really meet all of these demands with renewables by installing more solar, or do we still need using some of the natural gas power plants, or actually importing electricity from neighboring states, which can have not necessarily decarbonized power plants? But if we assume that we will be seeing a decline in emission intensity that is consistent with business as usual case from the IEA report, then actually we will also see a huge decline in overall emissions. So when we have a cleaner power grid and less use of gasoline, so we will see a quite substantial decrease in overall emissions, going down by 85% relative to 2019 in 2050. It is of course not still going to be zero, but it will be significantly lower in this particular case. But of course, we need to be very careful, because it will be very unlikely to see this kind of decline when we are adding 160 terawatt hour of additional capacity. And we are currently working on integrating with power system model to really understand what is a realistic case for this particular regulation. And the second piece I want to show you is about how much lithium-ion battery is required for these cases. In the first one, that business as usual, you can see there is an uptake of lithium-ion battery consumption in sales from battery electric vehicles, approximately amounting to 20 gigawatt hours in 2050, and the fleet level batteries addition will be approximately 200 gigawatt hour. But when we switch to the case of switching complete to electric vehicles, you can see there is a huge increase in lithium-ion batteries in sales from battery electric vehicles. The first question here is this plausible? Can we really get there? And here, by 2050, yearly sales will be 160 gigawatt hour of equivalent of battery. And the total fleet size will be 2,700 gigawatt hour of batteries. So if we can get there, then the question is, can we use these vehicles for vehicle to grid potential applications, like also using these to balance the grid? And another important aspect of this will be on the retired batteries and the second life of batteries. So if we are looking at these options, then the battery, so by 2050, we will be seeing approximately 1,100 gigawatt hour of battery retired over this period of time. So the next question will be about the material limitations, whether we will be recycling these, what kind of a landfill we need for storing these waste, as well as how we can use in second life applications. So these are just some of the analysis that we can quickly do, and also once we have the open access version open, you can play around with as many scenarios as you like. and create some of these cases and see the impact of different choices. And also, before finishing up, I just want to highlight that we have built this platform quite flexibly to be able to connect to different modeling tools, data sets, and other capabilities. And we have some ongoing work on connecting with other available tools and data sets that will be published soon. And here I wanted to show you a couple of papers that's been already published. And if you are interested and don't have access, please let me know. I'm happy to send you these. And here there is a list of papers that will be coming up soon at different stages of revisions. So just to finish up, so we are seeing a huge change in energy system, and we need to understand this from both pathway and system level analysis. So we need new tools to identify business opportunities and potential emission reduction options. A multi-platform approach is very key here, is because each tool has different advantages and strong suits, and if we can collectively use different tool sets, then we can have more accurate analysis. Basically, we also need to really understand the goals of different regions and match these goals to the regional resources. I will stop here. There is a huge team behind this, so I'm really appreciative of everybody's efforts, and I want to also say that it is impossible to build anything like that without having a huge and very good team. And I'd like I thank you for your attention, and Rob and others, if you have any question, I'm happy to answer.
Okay, and so let me reiterate that we're using the Q&A window, and so please ask away. Just as people get going and enter some questions, I'll keep an eye on them. Let me just sort of ask a little bit about your open source vision here, Emre. I mean, you're going to open source code. I guess that invites the opportunity for people to ask, or rather to modify it and perhaps introduce new industrial processes, for example, or new power generation technologies that could become part of the system. But I'm wondering also about the data. You point out that you get a very different answer for EVs in New York than you get in California. You'd certainly get a very different answer in Nigeria than you would in Massachusetts. Are you envisaging a sort of a big effort on the part of outside users to build a database? Is that a big part of the problem?
Yeah, so I think this is a great question. So in terms of the open sourcing, basically, as we've discussed, first of all, the energy system is not static. So it's developing every day, and this needs to be a community effort to keep up with what's going on in the scientific community. So for the new technologies, basically everybody can be able to build their own modules and submit to their modules to the like our committee to be part of the official version. And of course, in the data sets part, there's a huge data sets behind SESAME, and we started with publicly available data sources to be able to share with openly and transparently with the broader community. And so the way we are focusing on, and also we have efforts for expanding the scope from US to different locations around the world. So we hope that researchers around the world will also submit their data sets or hook their data sets to the tool, so that it will be growing faster than we can develop in our group.
Do you need a supercomputer to run it, or does it run on a laptop?
It depends on the type of analysis you are doing. Right now, it can run on a laptop, although you need a like high performance laptop. But basically, we are planning to use supercomputers for some implementation of artificial intelligence techniques to automate the data gathering piece, which can significantly reduce the time and effort on finding data sources and also checking the data sources for different applications. and also for the forecasting piece that you had some questions about. Basically, once we start optimizing these systems, we will need more powerful computers, and it will not be doable in a laptop.
Okay, I'm just scanning the questions now, and they're starting to roll in faster than I can even read them. The first one is about your modeling of the emissions associated with vehicle manufacturing. You talked about cars, passenger vehicles. What about heavy-duty trucks, which are a huge contributor to emissions? How well do you rate your fidelity in modeling that?
So we started with light-duty vehicles. So we are very confident about light-duty vehicle results, but we are currently building the heavy-duty vehicle modules. So it's not ready yet, but we are going in the direction of including heavy-duty vehicles, aviations, as well as marine transport. So I think for each one of these, we will have quite good representations in the next couple of months. But if anybody wants to contribute, we are more than happy to incorporate some other work going on.
You referred to it briefly at the end of your talk, but I gather what you're doing now is mostly ignoring the fact that there's an electricity network that you have to deal with and markets, and you're just looking at capacity and your ability to or rather the emissions associated with that capacity. So there's a question from Maria Ulick about the appropriate level of granularity and whether how far you have to go in modeling the network and taking account of transmission bottlenecks, for example, power flow reversals that may or may not be allowed before this really becomes a correct forecast or model.
No, I think that's a super important question. So basically, the level of detail we need is also can be understood from using the tool, because we also have capacity expansion models at MIT, and we know some of these issues with building new networks, so on and so forth. And so this, in its current form, it's giving a first order estimate of what will be the emission consequences. And the second piece here is how we can go from today to there, and what is the right path which will have minimum emissions. And for that particular one, actually, we are currently working on incorporating some capacity expansion models as well. But we really need to understand how much of a difference it will make to have these capabilities and solve everything together. Because as everybody knows, when we add more granularity, we are losing, we might add accuracy, but we are definitely losing computational efficiency. And here, one of the key focuses of SESAME is basically we want to get quick answers and run as many scenarios as possible and compare these options. In other modeling tools, you can get more accurate results, but it takes quite a lot of time to run it. And so actually you need to focus on a small set of scenarios or options. So I think there is a balance and trade-off there. So depending on the accuracy level that we need, we can always connect to the capacity expansion models, and we are having discussions with some of the developers for capacity expansion models right now.
Okay, so we have only a couple of minutes left. I'm going to try to combine a number of questions that I have with questions that I see on the screen into one in hopes you'll be able to sort of address it comprehensively. Hydrogen is becoming a really big topic, even just over the past 6 months. The possibility of shipping hydrogen around in the form of ammonia on ships and so on, which is becoming very topical just this month. And so there's this possibility of a transformation to a hydrogen economy. That's not a new idea in any sense of the word, but the idea would be, very deep penetration of hydrogen, not only into fuel cells for cars, but into industrial processes and many parts of the economy. All of that would affect the financial viability of pipelines, large-scale electrolyzers, large-scale storage facilities. I know you've been looking at these things. I guess the question is, what about the hydrogen economy? Can a tool like SESAME be used to model all aspects at the same time of that sort of transition, where everything comes into play, or do you have to look at it one line at a time? Or how would you handle questions of that?
So, yeah, so I think hydrogen is becoming more and more important, definitely. And we have a couple of ongoing projects about hydrogen in the global scope. And also we are collaborating with a joint program, Sergey Paltsev, about doing these kind of projections. And so with SESAME, you can look at the entire value chain from cost and emissions perspective. And also it is not only looking at pathways, because you can define systems based on these pathways. So for example, in a EU country, if you need to meet X amount of hydrogen demand, so you can build different options from different production methods, transport methods, maybe conditioning to different end use sectors, so on and so forth, and build a system and evaluate the environmental impact and cost of these systems. And then you can compare different systems. But on the connection with power system, for example, so I think Darik also presented in the webinar that we have also built another tool, a hydrogen supply chain model, which is an optimization model that takes into account the entire supply chain and optimizes for a given system what will be the optimal hydrogen supply chain network. So these are two different kinds of modeling approaches. And in SESAME, basically you can create many different scenarios to supply the demand for different applications. You can add new technology options. So for example, methane pyrolysis is discussed frequently. Can we use it? If we use it, how much of a difference it will make? We can easily add other transport methods like liquefied hydrogen tanks and see what will be the cost and emission consequences of these, and create basically different scenarios and assess the trade-offs of each one of these scenarios.
Okay, so but you're still following one pathway at a time. You're not having a hydrogen economy with everything going to hydrogen at the same time, for example.
No, actually you can. So basically, but it will have the pathway level resolution. But so you will build pathways to represent a system, and you can represent a hydrogen economy for different sectors, different applications using SESAME, and compare options like the one that we discussed about battery electric vehicles versus internal combustion engine vehicles. In California, you can compare hydrogen for decarbonization versus electrification of industry in different locations. And with SESAME, you can compare these two options quite in detail.
Okay, so I know you're just getting going with SESAME, and we've got years of development ahead of us to really make something that's completely comprehensive. But I introduced the topic by advertising the difficulty of imagining the cross-sectoral sorts of interactions and predicting the consequences of one thing happening in one sector reverberating throughout the other sectors. And so I guess the question is, what surprises have you seen? What's the most surprising outcome you've seen in the course of using SESAME so far?
So I think one of the surprises I've seen is about the electric power system. So we started with this California analysis and looking at startup and shutdowns and how much of an emission impact we'll see. The first surprise we've seen was actually most of the emission impact is due to hydro availability in a system like California and not due to cycling or startup and shutdowns. That was a very interesting observation for us, because basically it shows how much we rely on hydro and how much of an additional long-term storage we need if we have an incident like drought in systems that has hydro power. And also, when we started this analysis with California, we expanded to entire US. And the second interesting observation is actually we haven't seen any significant operational change that will have a meaningful consequences for the emission intensity around in the US. So I think California was kind of the only case that is really affected by the renewable penetration. Of course, it is due to having higher solar, but I was expecting to see something more around the US, and that's another really surprising result. The third result that was really surprising to me is the comparison of the vehicles from the actually mobility of the future study. So I wasn't expecting to see hybrids, plug-in hybrids, and fuel cell electric vehicles be very similar in terms of emission intensity. And also, whenever I was thinking about steam methane reforming for hydrogen without carbon capture, I still thought there will be quite significant emission consequences even if you use in fuel cell electric vehicles. And that was another shocking result, actually, that shows the potential of hydrogen in transportation as well. Maybe not for light duty, but there is definitely a big potential for heavy duty vehicles. So also in terms of industry, we are also doing quite a lot of projects about industrial decarbonization. One of the major points that we see is industry decarbonization is really hard, and it wasn't really thought of till this point. And now I think there is a panic mode everywhere, and everybody is trying to find a solution that will completely decarbonize industry. Unfortunately, this will not happen. We need a portfolio of solutions, hydrogen being one of them. And I think with SESAME, we are really prepared to explore these options. So for heat demand and for other feedstock demands, we can easily swap different options and show the impact. And I'm really excited about some new projects that we started about industrial decarbonization.
Okay, that's really interesting. I'm looking forward to hearing about more surprises and more opportunities. I think you've already given us some direction for hybrid electric vehicles and fuel cell vehicles. We've gone a few minutes over already, so we really have to wrap up now. But I'd like to thank you, Emre, for taking the time and showing us this really important work, and to wish you well in developing it further. We're looking forward to seeing that public version come out. Thank you, everyone.
Thank you very much, Rob.